day and have an absolutely amazing nap.
They have changed things, so I don't know how to make this closed caption. That's weird. Okay. Today we are talking about telescopes. This is the first section of our space part of Earth space science. The standard is that we hope to construct an explanation detailing how space can be studied by observing all the frequencies of the electromagnetic radiation with differentiated telescopes and observational tools. The three things we're going to do, hopefully today, are explain how astronomers use the whole electromagnetic spectrum to study the universe, to identify the different types of telescopes, and to describe historical and modern observations made with telescopes. So, here we go. Astronomers are simply scientists that study the universe beyond Earth. That's what we do. Unlike other scientists, like biologists and stuff, they can study their stuff right there in front of them. Astronomers can't really do that because everything is way too far away. So we can't study our subjects of research hands-on in the lab. Instead, we have to study stuff as astronomers that are way too far away from where we are. Hopefully you are all filling in the blanks as you go. Are we good? Who left me a phone? It's plugged into one socket over here and it's out in my class. What is it? What kind of phone? I have 11. I was hoping you had a 12. I was just going to switch them out and you never noticed. No, you wouldn't notice it. Just because, yours has a picture of, I don't know who that is on the front because I couldn't really see it. And mine has a picture of my old dog on the front. You wouldn't. So how do astronomers do that if they can't get there and actually physically hold the thing in their hand to look at it? Well, they use light in a lot of its different forms. Because light can travel through a vacuum or empty space, it can get to us from very, very, very far away. Electromagnetic radiation is simply energy that is transmitted through space as a wave. And light is one of the forms of electromagnetic radiation. Yes, you don't have to always type. I would like you to type electromagnetic if that's what you needed to. This time, from here on out, if you wish and you can remember, you can just type EM when you have to type electromagnetic. All right? As long as you remember that EM stands for electromagnetic. Light is the fastest thing in our universe. Light travels at about 300 million, right? Meters per second. Per second. Which is about 186,411 miles per second. Now that's not miles per hour, which would be impressive enough, right? 186,000 miles per hour, that would be crazy. But no, that's per second. to help you understand how fast that is, if that light started in New York and went back and forth from New York to the west coast of California and back, that's what it was doing, all right? It could do that 40 times in 1 second. That's how fast light travels. So a light year is how far light can travel. I know. In a year. Surprise! You never would have figured that out, I'm sure. Because that one's really hard. A light year, do you see all those zeros? 1,000, million, billion, trillion. That's 9,500,000,000,000 kilometers. Or 1,000, million, billion, trillion. 5,900,000,000,000,000 miles a year. Crazy, right? Proxima Centauri. You know that our sun is a star, right? And you know that our sun is the closest star to us. So besides our star, besides our sun, the next closest star is Proxima Centauri. And Proxima Centauri is 4.22 light years away. So it takes the light, if Proxima Centauri, okay, put it this way. If Proxima Centauri went out today, we would still see the light from Proxima Centauri for about 4.25 years before it just disappeared. Okay, does that make sense? All right. Our galaxy, the Milky Way galaxy, in case you didn't know, we are in the Milky Way galaxy. Our galaxy, from one edge of our galaxy to the other edge of our galaxy, is 100,000 light years across. So if we were on that edge and something at this edge went off, it went black, we wouldn't know it had gone black for 100,000 years. Because the light would still be coming to us from that far away. And look at how fast it travels. So that tells you they're like huge distances away, right? Okay? When we look at stars and galaxies, what we're looking at is their past. We aren't looking at what they look like right now, because they're so far away. The next closest galaxy is the Andromeda Galaxy. All right? And it is 2,500,000 light years away. So when we look up and we see Andromeda, and we're studying all the stuff that we're studying about Andromeda, we're studying what it was like 2,500,000 years ago. So astronomers really are space, what's the word, the A word, anthropologists. They study the history of planets. They don't think of it as the history of planets because they're studying it right now. But it's really what was happening on that planet, however far away, however long ago that light started. Does that make sense? Yes, no, maybe? Okay. know that light travels in electromagnetic waves. And the two components of electromagnetic waves are, I know, you'll be shocked. There's an electric field and there's a magnetic field. I know, so shocking and surprising, right? The two fields move between positive and negative values. They don't travel like this. They actually travel in waves, like this. Well, actually, one of them travels like this, and the other one travels like this. So one goes up and down, the other one kind of goes sideways. Okay? Are we good? I did not hear a no, so I'm assuming that's a yes. So the way we look at electromagnetic waves is we look at their wavelength and we look at their frequency. A wavelength is the distance between the crests. The crest is the very top. The highest point of a wave is the crest. And we go from the crest of one wave to the crest of another wave. And that is called the wavelength. The frequency then is how many wavelengths pass a point every second. If you think of a wavelength as traffic, like 465. I don't know if have you guys ever driven on 465? Or, okay, maybe you haven't driven, maybe you probably have that. I don't know. Have you ever ridden on 465? Okay, or even 69, like to Indianapolis. Okay, you know, sometimes there's not much traffic and you can travel pretty quickly, right? Well, wavelengths are kind of the opposite. If there's lots of space between them, they're moving really slow. So if I have a wavelength and I've got one wavelength like here and another wavelength way over here, this is a really slow wavelength. It's taking its time. So its frequency, and if I've got a point right here where they're crossing, its frequency isn't going to be very high, right? Because there aren't going to be very many waves passing this point. But now think of 69 or 465 during rush hour traffic, where it's back-to-back cars, right? Now, all of a sudden, I'm going to have lots of traffic through this point. So the frequency is going to be higher. They're also going to be closer together. Does that make sense? Yes? Okay. Visible light is the light we can see, and everybody kind of probably goes, duh, because you probably already heard this like 1,000 times. It's any light we can see with the human eye. It comes in lots of different colors. And those colors are based on their wavelength. If you look over here, you can see the longer wavelengths are in the red and orange, and the shorter wavelengths are in the blues and purples. Okay? Oh, sorry, I'm going to go backwards. We also know that there are longer and shorter wavelengths in the electromagnetic spectrum. The problem is we can't see them. Anything beyond that little, see how thin that part of visible light is? I mean, it's, get out of my way. This is the spectrum. This little teeny tiny space right here is the visible light. That's all we can see. Unless we use tools that help us do it, help us see farther. And astronomers do that because they actually study stars in the entire spectrum. There are some really hot stars that emit mostly ultraviolet rays. We can't see those stars unless we use a special telescope. Some are really cold stars, and they emit in the infrared ray. Or infrared, not ray, infrared spectrum. If it gets extremely hot stars, you notice gamma rays are way down there. So if it's really hot, it's going to get into the gamma ray section. And if it's really cold, it's going to be way over here. And that's going to be in the radio waves section. Bless you. You good? Much of what we study can't be seen with the naked eye. As I just said, bless you again. It's a section or a spectrum that is outside of that visible light, so we can't see it. So instead, astronomers use telescopes. And everybody probably kind of goes, duh, we already knew that. Okay? But did you know that that's why they used them? So they could see beyond that visible light spectrum? Yeah, it makes things bigger too. And it makes things, pulls things closer, but it also lets you see beyond the visible light. So now the telescope section, this is the major portion of what we're talking about. Galileo Galilei was an Italian scientist and mathematician. A lot of people think he invented the telescope. He's the one who became most famous for it in 1608. It was a refracting telescope, which means that it used lenses. It uses, just like those of us who wear glasses, we have lenses in our glasses. Those kind of telescopes use these kind of lenses to help bring that light into focus and to bend that light. Yes, there's lots and lots of improvements. Most amateurs still use a refracting telescope because they work really well for things inside our galaxy. Yes, ma'am. If I have time at the end, I will try to do that. Okay? Are we good? Then in 1670, along came Sir Isaac Newton. And Sir Isaac Newton built a different kind of telescope. This kind of telescope is a lot lighter. It uses mirrors instead of lenses. And it's called, it uses mirrors, so it's called a reflecting telescope. And it uses a concave mirror to help it collect and refocus that light. Because they're using lenses instead of mirrors, they are a lot lighter and they're a lot easier to care for. You only have to keep one side polished and clean. as opposed to lenses. Okay, those of us who wear glasses. If I just clean the outside of my glasses, if I never clean the inside of my glasses, am I still going to be able to see really well all the time? Why not? Because the inside is still going to get dirty and cloud up, especially with these wonderful masks. They fog up all the time, which is why we try to come up with new ways to hold them so they don't fog up. All right, so we have to clean both the inside and the outside of a lens. Same way with the telescope. But if you have a mirror, who cares what the back of that mirror looks like? You don't use the back of a mirror, right? You only use front, so you keep the front nice and spotless and shiny. So since they're lighter, we can make them bigger. And bigger is better because if it's bigger, it can collect more light. That means I can study things that are really far away and really, really dim. Okay? The largest optical telescopes are those reflecting telescopes. Notice I said optical telescopes because there's bigger ones. They're just not optical ones. We're good? This is a catadioptric telescope. It uses both. It uses both lenses and mirrors. And it has a shorter tube. So it's a lot more portable because it's smaller. So you will also, some amateurs will also use these, but they're a lot more expensive. Oops. Come on. Oh, wait, back. There we go. So all of these telescopes that we've talked about so far collect and focus visible light. Only visible light. So that little itty bitty tiny part of the electromagnetic spectrum. To collect light at longer or shorter wavelengths, I need something that's going to allow me to do that, to see those extra spectrums. So they use radio telescopes. Remember I told you there were bigger ones? These are the bigger ones. Radio telescopes are huge, and if you look at them, they look like satellite dishes, right? Like the satellite dish that might be on a house. Okay, you can't say to get the cable because, well, cable and satellite, two totally different things. But to get TV reception. And they look like that and they act like that. That's what they do. They collect the light or the radio waves or the microwaves. All of those, they can collect any of that. The largest single telescope is this one here. It's in Arecibo. It is the Arecibo Observatory in Puerto Rico. It is a fixed telescope. It is so heavy and so huge. It's actually in a sinkhole. They built it in a sinkhole. And it is big and huge, as you can tell. And the downside to it is it can only observe the sky that's right there. That's it. But that's a lot of sky. And hello, our planet isn't still. Our planet rotates. So it sees a lot of sky, right? It can't see the sky down here, though, and it can't see the sky over here. but it's still seeing a lot. Sometimes they'll get a whole bunch of radio telescopes and link them all together with a computer, and they'll observe the same object with all of these telescopes, and then they kind of meld the images together to get a clearer, more precise picture of exactly what's going on in that area. Good? So the problem with telescopes that are here on our planet is our atmosphere. Now, we love our atmosphere. We want our atmosphere to stick around. Thank you very much. But there is a problem with it, because as the electromagnetic radiation passes into Earth's atmosphere, the atmosphere does its job. It blocks some of those rays, which is a good thing, because otherwise we would all fry, right? So it blocks a lot of that UV and higher radiation, and it blocks some of the infrared radiation. And hello, our atmosphere, because we've already studied weather, we know that our atmosphere is constantly in motion, right? So because of that, that motion distorts the light rays, the waves. And so it makes the pictures that we get a little fuzzy. So that's a problem. There's a solution. Anybody want to guess? Oh, come on, this is an easy one. What would you do?
Telescope in space.
Put a telescope in space, and that's exactly what they did. They used space telescopes. These space telescopes can carry instruments that will observe the electromagnetic radiation in all frequencies. This particular telescope that we're looking at here is called the Chandra X-ray Observatory, and I am sure you never would have guessed that it observes in the X-ray spectrum. Never would have guessed that by the title, I'm sure. It's a surprise. It's really hard. These pictures that are underneath it are actually pictures that have been taken by the Chandra Observatory. I know they don't look like the x-rays that we get when you have to go to the doctor and you break your arm and you have to go to the doctor and they take an x-ray. They don't look like that. Kind of wish they did, because that would be much more entertaining. But these are pictures that were actually taken by the Chandra X-ray Observatory. Kind of cool. Again, not anything we would be able to see with the naked eye. The most famous of all of the space telescopes is probably the Hubble Space Telescope. I can't even say its name. It was put in orbit probably, I'm trying to think, probably before y'all were born, right? 1990? Were you born in 1990?
It would make us like 30.
Yeah, okay. Yeah, you're right. Duh. You either failed a lot of school, but you look really good for 30 years old. I'm just saying. Okay, 1990. I was 30, by the way, in 1990. So it was put into orbit in 1990. I'm sorry, my kids were born then, so I assumed that all children were born. But yes, I could be your grandma. These were put into orbit in 1990. Then they figured out that there was a problem with one of the mirrors. It had a flaw, and so in 1994 they launched another space shuttle, and they were able to go up and actually change out the mirrors. And that telescope is still in operation. As of 3 weeks ago, it was still in operation. It is still out there. All right. Now, I will tell you that they have been since 2018, they have been talking about and trying to get this together to launch another one. It's called the James Webb Space Telescope. Because Hubble is getting old. it's getting really old. But it's still functioning. Now I will say that a couple of weeks ago it kind of went into safe mode and it stopped doing its job. But strangely enough, they were able to repair it from here. It was a computer malfunction. And they were able to fix it from here, and it's starting back up, and we're getting pictures again. Yes, it's over 30 years old, which most of you know for technology, 30 years old is ridiculously old, right? But it's still working. James Webb, they're working on it. They were going to send it up in 2018. They're still working on it. Hopefully they will be able to get it up before Hubble stops. These, by the way, are some of the pictures that we have gotten back from the Hubble Space Telescope. We know that humans have been studying the sky for thousands of years. They watch the motions, they watch patterns in the lights, they use the rhythms of the sky to know when to plant their crops, when to harvest their crops. They use them to time their religious ceremonies. They just really watch the sky, and it helped them understand things about nature. Are we good? Okay. There were some ancient Greeks who actually went along and actually plotted the stars. They would make drawings of the stars in the skies where they were. They noticed that some stars, and you notice that stars are in quotes, moved. They didn't just stay stationary, they moved. While others of them kind of didn't. They stayed in place. The stars that moved, they called planets. Planets, and it was a perfect name for them because planets in Greek means wanderers. So these planets were wandering the night sky. Now, of course, we all know that they don't really wander the night sky. They travel, they orbit. Okay? We know that planets, now we know, folks, oh, please no. Planets aren't really stars. There's a difference between a star and a planet. You guys know that? Yes, no, maybe? Okay. But there are other stars out there. Our sun is a star. Earth is not. But Earth from another planet could look like a star because of the light that's reflecting from our sun, right? Okay, we good? Greeks also then started drawing things in the sky and connecting stars. And they identified planets of those stars and they called them constellations. And they started making up stories about these constellations that fit with their culture. Orion was a hunter. And so when you look in the night sky, you'll see a curve of a bow, but the thing that will help you find Orion is you see 3 stars right in a row, and they're just one direction. I can never remember which way. From the North Star, but you see 3 stars in a row. And that's called Orion's Belt. And once you find those, then you can kind of follow to the other stars. Then along comes Galileo. Well, before Galileo, there was somebody else, but we're going to talk about him in a minute. Galileo became such a famous astronomer because he was the one that discovered there are more stars that can be seen than what we can see with our naked eye. He noticed that the Milky Way, our galaxy where we live, is really a big, huge band of lots and lots of stars. Our star is not the only star in the Milky Way galaxy. He also saw for the first time that the moon has craters. I mean, if you look up in the sky when the moon's out there, you can see some dark spots and you can see some light spots, but you can't really tell that they're craters, right? Well, he has this telescope. He's the first one to discover the craters. He also discovered that Venus has phases just like our moon does. Kind of makes sense if you think about it. He also is the first one to see Jupiter's moons and to know that these moons were actually orbiting Jupiter. And he saw that there were dark spots that actually move across the surface of our sun. It was Galileo's observations that helped support Nicholas Copernicus's model of the universe. And Nicholas Copernicus was the first person to say that the sun was the center of our universe. It was the center of our system of planets. And we actually revolve around the sun. And everybody in here is going, well, duh, we already knew that. They told us that way back in, 3rd or 4th grade when we first started studying the planet. Yeah, that's because we're smarter than they were. Actually, it's just because we learned more. Until the early 1500s, people actually believed that everything revolved around Earth. We were the center of everything. Because we were so important. Everything revolved around Earth. And then along comes Nicholas Copernicus. Oh, by the way, that is called geocentric. Geo means Earth. Centric means center. So geocentric, Earth is the center. Right? Then along comes Nicholas Copernicus. And he starts studying the night sky and he realizes, oops, actually, we aren't. The sun is actually the center of our solar system. And everything, including us, revolves around the sun. We orbit the sun. And then, we do have something that orbits us, that loves us enough to orbit us. That's why it does it, because it loves us. It has nothing to do with gravity. Right? Because we do have the moon. The moon hangs out with us, right? But everything else, including us, we orbit around the sun. That's called heliocentric. Helio means sun. Centric still means center. So heliocentric, sun-centered. Right? By the way, Nicholas Copernicus was not at all popular for that idea, especially with the religious people. Because the religious people of the time believed that God made us, and so he didn't make other things and other people, so we were the center of everything, as we should be. Right? And then Copernicus goes, and they were not happy. We know that all light is composed of lots and lots and lots of different colors. How many of you ever played with a prism? Anybody? You know what a prism is though, right? Okay, if I take a prism and I hold it in front of just white light, it will break that white light into all the different colors that actually make up the light, right? Well, scientists use those too. They call it a spectrometer. It's a piece of equipment that actually has a prism and other different things that will break the light into its component colors. And they can use that data to figure out how hot the star is, Because remember, if it's got lots and lots of the blues, it's going to be really, really hot. They can tell what elements it contains because each element gives off its own color of light. Kind of weird, but it does. They can tell how fast it's moving, and they can tell whether it's moving toward me or away from me. If you watch the videos from yesterday, they explained that red shift and blue shift, right? Are we good? That's the last one, right? Okay. Do you have any questions? Yes, ma'am. Yes, remind me. Hang on, let me stop the recording.